our grant with the Hinkley Center. So with that, hopefully all of you can see my screen who are online. I know there's a couple people who are going to be coming in the room shortly, but what we'll do is we'll start with, first of all, a welcome and some introductions. So I'm Tim Townsend, professor at University of Florida. We're here for a TAG meeting, or a technical awareness group meeting, for the a research project that we're currently conducting with the Hinkley Center. You can see the title, Looking Beyond Florida's 75% Recycling Goal, Development of a Methodology and Tool for Assessing Sustainable Materials Management Recycling Rates in Florida. I'd like to thank all of you for participating. Before I kind of introduce the rest of the team who will be presenting today, what I'd like to do is, for those of you here in the room, if you don't mind just giving a real brief introduction, and then I'll read off the list also of who's online. But Tina, maybe I'll start with you.
Hi, Tina Corey. I wear two hats. I'm executive director of the Florida Recycling Partnership, and I also work with the National Waste and Recycling Association, Florida chapter of Memorials.
I'm the Waste Management, Government Affairs Manager based out of the Central Florida area, and here to kind of listen and learn. Thank you.
Suzanne Moore, FDEP.
Travis.
Hey, Travis Barnes, I live in County Solid Waste.
So with the Klein with Jones and Associates.
Go in the back over here. You guys, not Beatrice and Preston.
Oh, Chance Gregory, University of Florida.
Kyle Beer, University of Florida.
Helen Bear, University of Florida.
Kevin Vance, Smith.
And
John Sherry.
yeah, so again, this is a project funded by the Hinkley Center for Solid and Hazardous Waste Management. So certainly want to acknowledge them, and then Wes Anderson, who helped get everything set up for us today, and of course the DEP and the legislature, whoever else funded this research ultimately. Today, most of the presentation is going to be done by students, primarily by Malakan Chassi, who's a PhD student. She'll come up here in a second, but then Beatrice and Carson are both going to present at some point. I'll let them introduce themselves a little bit more, all three of you, when you guys come up, and maybe you can state what you're working on in terms of master's student, PhD student, and all that kind of stuff. The goal for today is that we're going to review a current Hinkley Center project, but it's a little difficult to do that without providing some broader context in terms of some of the research that we're doing. Most of you in here know about this term sustainable materials management, but it's one of a number of terms that allows us to think about looking at transitioning from waste as just a material that we have to get rid of and manage, to looking at materials over their entire life cycle. As I say that, let me just quickly acknowledge those of you online. I apologize, but I think Richard Tedder, we've got Richard on the line, David Gregory with Orange County, Dawn is on the line, Dawn McCormick of Waste Management, Keith Howard of HDR, and then Ron Bellotti. I think I heard your voice earlier too, Ron, so thank you all for coming. And then, since you guys just walked in, introduce yourselves real quick. So Karen and Jennifer from DEP are here, so we're all complete. So thank you, everybody. So again, back in 2016, we did a research project, and it was called kind of State of the State. We were looking at current state of solid waste management, state of Florida, kind of with this looming 75% recycling goal in mind. Malik's going to give you a bigger recap of what was done there. The one in the middle on this slide that says 2019, that's the project that you hear about today. And so we're going to give you an update. It's kind of a little bit of a follow-up to this State of the State project. A lot of times I'll call it State of the State 2, but we're working on that. As part of that State of the State project, many of you in this room participated, or on the call, participated in some of these work groups, and so we're trying to keep that momentum going. I did want to point out that kind of in the interim, we've also been working a lot with the department on this program called WasteCalc. WasteCalc is something that you'll hear more. Carson will come and give you all the details about it, but it relates to what we're doing with regard to the recycling goal and alternative ways of looking at managing materials in the state of Florida. We did some work last year on that. We're currently doing some work on that right now. And then lastly, the last project that's listed here is that we'll be presenting to the Hinkley Center's Research Selection Committee this coming week to review for another project that relates to all these topics that we're going over today. Okay, so what we'll do, we've been through our introductions and agenda, although I'm going to do a little bit more agenda slide in a second. Mock's going to come in, she's going to really give us a brief, or not a brief, but a pretty good thorough overview of what was done before. We'll talk about the new projects, the project that's underway right now, which some of you are a little bit familiar with, some of the things we still hope to do as part of that, then talk a little bit about next steps in the future. So again, apologize that we changed the time around on a little bit. We had another tag meeting about ash recycling right before this, and so to help us with that transition. Our goal is that we'll have 15 minutes or so at the end, although to be honest, in the last meeting we ended up talking more. I probably already exceeded my allotted time amount. But hopefully we'll have plenty of time. And since there's nothing after this, for those of you who are here, we'll stay as long as you want and talk as long as you want. Again, I'll let Malik come up and kind of give you an overview of maybe what led to where we started, why we started, and then what we learned that first year, where we're going.
All right, how are you guys doing today? Good, hopefully. All right, thank you all for joining us both in person and online. We appreciate your feedback. It's always been tremendous in getting us more direction towards where we're going with both of our projects and hopefully our next project as well. So my name is Medican Chelsea, and I am a PhD student at the University of Florida with Dr. Townsend. I've been working a lot with this idea of sustainable materials management and being able to quantify it in a way where you would be using it in policy and actually decision making. So with that in mind, we're going to take a few steps back to 2016 and start discussing the Florida Solid Waste Management State of the State project that we started. So we started this in 2016, and that was about 4 years before our 2020 75% recycling goal. And quite big a motivator for us to be able to, one, look at Florida and try and understand its mass flows, its generator flows, and the material flows that are going through it. There's a lot of work that DEP has done and put into being able to quantify our recycling rate and the amount that's collected, but there were still some gray areas with respect to how much yard trash is associated with a resident or a non-resident. So we tried to do this by expanding onto what DEP has done and be able to estimate for each material and each management exactly where it's going. So combusted, landfilled, recycled. And then along with that, something that we had in mind was to quantify the costs associated with Florida solid waste. There's a lot of feasibility studies that are able to tell you for this specific facility, it costs this much for a cost per ton. But there hasn't been any type of work out there that focuses on the whole state of Florida and is able to quantify and say that this is our solid waste management cost. This is what we have been paying for, both associated with each generator type and each material. So along with that, there is something that we wanted to look at, and that's the idea of using these life cycle models, which are just a way of quantifying your environmental impact. So there are two that we really focused on: greenhouse gas emissions footprints and then energy footprints. We were able to do that, and for the 2016 year. So knowing that we have this portfolio of greenhouse gas emissions and energy cost and then all the solid waste mass, now we're able to see, well, if we were trying to aim in 4 years to reach the 75% goal, what are a few different types of scenarios that we could do? And we looked at a few potential scenarios to see their impact on the recycling rate, their impact on the environmental footprint, and then their impacts on cost. And then something else that we began looking at more and more since we started diving into this idea of life cycle and really looking at the footprint of each material is that, you know, not 1 ton of aluminum cans is necessarily the same as 1 ton of C&D debris, although we do treat them that way when we're going after the recycling rate. So we began incorporating LCA and SMM into waste goals. So what we'll do right now is just go through each one of these points and be able to really dive through to see what we learned last year and how this project ended up being concluded so that it moves on to this next one. So looking back at the recycling rates in Florida, you notice that there's a lot of steep increases and decreases. And it's not because suddenly we're increasing our recycling rate by recycling more, or we suddenly stopped recycling everything, but it's really a matter of accounting. And one of the big differences in accounting that we included back in 2010, 8, around that time, is that renewable energy, which is representing that orange line, or those orange bars. So starting from those years, we were able to include waste to energy credits, yard trash used as yard trash gas, or MSW used to generate MSW gas. And it was dramatic in our impact to reaching that 75% goal, but still in 2016, we were still only at 56%. So what we wanted to do then is kind of look at the 2016 mass and be able to understand the disposition of each materials and the generator types. We broke these up into 4 different generator types: residential, non-residential, yard trash, and C&D. Typically, C&D and yard trash are already included in residential and non-residential, but we believe that they were a unique enough category where we were able to break them apart from residential and non-residential. And from this, you could see that the residential are the most contributing generators towards our 37.4 million tons generated in 2016. And then from that, you'll see that we have these 3 different types of recycling rates. You're already familiar with the total recycling rate. That's something DEP already quantifies, and that is where you're including those renewable energy and any type of traditional credits. So those traditional credits are referring to things that are used as landfill covers or process waste. So it gives you a little bit more bump if you're about to use a mixed glass or some type of other material into your landfill. You could count that as a recycling credit, even though it's in your landfill. And then your standard recycling rate is something that we created. And that standard recycling rate just is an envisionment of, if you were to take this aluminum can or this cardboard box and actually send it to a MRF and recycle it, that is what you're getting. That is your recycling rate. So you can almost imagine 100% recycling rate as everything that's sent into a MRF and then recycled.
Just real quick, for those of you who are on the line, we're getting some feedback that maybe the audio is cutting in and out. If you could please mute either your phone or your computer, I think that might be causing some of the audio difficulties. I can hear some shuffling of the desk and stuff. Thank you.
So diving into those recycling rates a little bit more in detail, we can see that the standard recycling rate really is that representation of the actual materials recycled mass. And then when you look at the traditional recycling rate, you're taking some of that mass from combusted and landfilled, and it's counting towards your recycling credits. And then even more so, you'll notice that nearly all of the combustion tons are really counting as recycling credits. So I know you guys are mostly familiar with these because you've been dealing with them for quite a long time, but it's always good to get a little refresher to understand exactly what's happening with our waste stream and how we can better manage it. So unsurprisingly, the materials with the largest recycling rates in 2016 were those that were heaviest. So like scrap metals from ferrous and non-ferrous, white goods, C&D, and then yard trash. It would make sense because a lot of county recycling coordinators will be going after materials that have the heaviest impact on the recycling rate. So they'll be targeting those types of establishments that are recycling metals or concrete, recycled asphalt, pavement, and then white goods also. So kind of going back even more, we want to get a better understanding of how all this mass is flowing. Now that you know these numbers, where are they really going and what's happening with them? So this is for 2016 and for the whole state. You'll notice that these are the same numbers you saw earlier, the residential collection, non-residential, yard trash. So it makes up a total of 26.2 million for 2016. So of the residential and non-residential, and this is also yard trash, we estimated about 18.6 million tons are sent to a transfer station. And then from there, some of this material is actually sent to a waste to energy facility where it is combusted, and then there's ash that is recovered for metals recovery. And then from there, there's also ash that is sent to a landfill. So right now there is about 10.5 million tons of MSW landfilled from all 3 generators. And then furthermore, when we get into the recycling, you'll notice that there is about 5.9 million tons recycled. And then for the yard trash flows, a lot of it will either be composted to be used as compost and sold, or it'll be mulched and just placed on top of a landfill. And that is about 3.2 million tons. So now looking into the C&D collection, we treated this one a little differently. We didn't actually, we were able to actually estimate how much was collected based on those generator assumptions that we made previously in our study. And from there, we were able to see that about 4.5 million tons were landfilled, and then the rest were recycled. So C&D does have typically one of the highest recycling rates out of all of the materials. Looking at these recycling rates again in depth, you'll see that standard recycling rate, which is just telling you how much is actually being sent to the MRF and then really recycled. The traditional recycling rate, which gives you any credits for landfill cover usage or process fuel, and then the total, which is including renewable energy or any type of landfill gas energy. So even with all of this, we can see that we're still not really reaching that 75%. Yard trash does reach 75%, but you have to remember that yard trash is not actually allowed to be placed into a landfill in the state of Florida, so it would make sense that it would be reaching such a high recycling rate. Although when you look at things like the residential and non-residential, you'll see that the standard in the traditional recycling rates, the ones where where the residents or the non-residents for commercial establishments are putting out their materials on the curb or in the recycling dumpster, they're still really low. So it's telling us that there is a lot of target potential for us to focus in on those types of generators. So with that in mind, we also wanted to take into consideration the costs associated with solid waste management in Florida. So for all of those mass flows that you saw earlier, we just attached a dollar value. I know it sounds really nice and easy, but it wasn't that nice and easy. So what you're seeing is our labor or fruit of labors or whatever that idiom is exactly. And you'll see that a lot of the cost is focused in on the cost of collection. So recycled MRFs, it's actually, I know it's showing you that there is a cost savings, but that's because it's breaking apart from the cost of collection. So that recycling cost of collection is already included in that 700 million number. So if you were to break that apart and add it back into the MRF number, you would probably see that it's not a cost savings. And this is in mind with 2016, so you can imagine that nowadays, this 2019 number, you're going to have even maybe potentially a loss or a cost associated with it. Then another thing that we wanted to look at was also the cost associated with C&D. We didn't look at the collection cost of C&D because it's so variable, and we weren't able to get as great cost numbers on that. So what we focused in on instead was the cost associated with C&D landfills and then the cost to process these MRFs. So with that in mind, we had a total cost of about $3.2 billion, and that is including the cost of transfer stations. So taking that waste and it being transferred into a transfer station and then sent out to landfilling or combustion or recycling facilities. But if we weren't to include that transfer station cost, it would be about $2.9 billion. And it still shows you that the majority of those costs were from collection. So now that we have this portfolio of our masses and our recycling rates, we were able to have great discussion with you guys previously into deciding what types of approaches would be most, I guess, advantageous for us to focus on so that we are able to reach that 75% recycling rate. So we looked at 5 of them: the waste to energy approach, the mixed waste processing approach, the mandatory residential curbside recycling approach, the mandatory construction and demolition and yard trash recycling approach, the mandatory non-residential food waste, and composting approach. So these approaches only were applied to counties that had populations greater than 150,000. And I'm just going to go through each one of them, kind of talk about what we did with them, and a little bit about their feasibilities. So with the waste to energy approach, we assumed that of the 11 existing waste to energy facilities, they would be able to expand their capacities and accept waste from the counties that have 150,000 or more population. Furthermore, we also assumed that there would be new waste to energies built in Duval, Orange, Polk, Brevard, and Volusia County. So they would also be contributing to the consumption of the waste from other neighboring 150,000 counties. The impact of all of this on the total disposition, you could see that the combustion went from that 12% previously to 29% of the total waste stream in Florida. So it did impact it quite dramatically from that perspective. But when we start talking about things like feasibility, you'll notice that waste to energy, it's very economically costly. So from an economic feasibility, it won't be as easy as you would think to expand the abilities of those existing waste energy facilities or just to build new ones. Politically or legislatively, I wouldn't say that it would be the most difficult thing to do when you're comparing them to the other approaches that we'll talk about later. So another thing that we looked at was this idea of a mixed waste processing facility. So that's that dirty MRF idea where you would take your garbage and you just throw it into a facility, and this facility would be able to segregate your recyclables from your garbage materials, and it would just do most of that work for you instead of having the separate single stream and dual stream. And this approach, though, we did assume that the single stream or dual stream, the current recycling, would stay the same. We wouldn't impact that, but instead some of that mass that is sent to the landfill would be instead sent to a mixed waste processing facility. So we use this example from a facility in California. They assumed that they would be able to build a medium size and a larger size, which is why you see those the two size differences in the boxes. And then while having that, they were able to reach a 56% residential recycling rate and a 48% non-residential recycling rate. So doing that, you'll see that the recycling rate increased from that 44% to 57% of the total waste stream. So the blue part got much larger. Actually, the feasibility, though, of the mixed waste approach, I think it is a little difficult to say because there will be some reports that tell you that, this mixed waste processing facility is foolproof and you could definitely do it, but then there will either be case studies where they'll show you that the mixed waste processing facility didn't do as expected or was not as successful as expected. So the feasibility of this is a little bit ambiguous, and we weren't able to directly be able to say that this is a 100% doable approach, but we still wanted to look at the potential of its impact on the recycling rate and then later on cost and the environmental footprint. So mandatory residential recycling approach. This is where we were assuming that those counties would be able to meet a recycling rate of 64%. 64% was taken from the Seattle recycling rate in that year. So Seattle does have a mandatory recycling rate. Obviously it is a city, so it's a lot easier to control that than the whole state of Washington. However, they were able to have that and actually be able to reach a 64% recycling rate. And I believe they have similar goals to us in Florida, around 75% by, I think it was like 2025 or so. So using their model and using their recycling rate, we just assumed that, well, if these counties are able to 64% recycling rate, what is that impact? And the recycled percentage you could see also increased. It went from that 44 to 55%. The feasibility, though, of a mandatory recycling approach, I think you could tell would be very difficult, especially when it comes from the legislative perspective. Anything that is mandatory by ordinance or county ordinances isn't the most simplest thing to pass. So there could be some challenges when it comes to that front. So then the second mandatory thing that we looked at was the C&D and yard trash. This, like the previous one, would also be difficult, and from a legislative perspective, it might be a little bit easier since it's just a certain waste stream with C&D and yard trash. Here we looked at increasing the recycling rates to 77% for C&D and then 97% to yard trash. The 77% comes from the Los Angeles, their mandatory ordinance. So in Los Angeles, they were able to assume or estimate a 77% recycling rate for their C&D. And that was mainly because they passed a legislative ordinance where the city, anybody who was building any type of construction or demolishing any type of construction, they were required to send it to a certified C&D recycler before it could be disposed of in a landfill or combusted. And then the yard trash, the 97% comes from the city of San Jose, and they have a mandatory composting and yard trash collection where they partnered with a different organization to be able to provide the residents easy access to the composting facility and collecting their yard trash and materials. So this also increased the recycling rate as expected. It might not be as large as the other ones. And then the third mandatory thing that we looked at was this non-residential food waste composting. So you could think of it as like restaurant composting. And we used a assumption where the non-residential food waste for those counties would increase to, their food waste recycling rate would increase to 58%. So the first thing that jumps out is kind of like the recycling rate didn't really increase. It was 44, now it's 45%. The big reason why is because these counties that are already recycling or recovering their food waste, there's not as much mass available. So going to a 58% recycling rate wasn't as dramatic as if we were to go to a different recycling rate, such as 75 or 80%. But the reason why we chose 58% is Seattle also happens to have a mandatory restaurant, commercial, non-residential composting program. So we wanted to replicate or model something that has actually been successful, and with that in mind, we took their recycling rate. So they were able to meet a 58% recycling rate. So applying that here, it wasn't as big of a difference compared to the other ones, but it's still an idea that I think many people want to explore, especially when it comes to food waste. So looking at the recycling rates, again, this is just an increase by percentage points. So the waste to energy increased their points by 13%, then 10, 8, 7, and about like 0.5% for the last one. I think this tells you that no matter what you do with an approach, that it's going to be very difficult to reach 75%. What we would need to do to really reach it is probably a combination of these approaches, but knowing the feasibility of them, it's not necessarily the easiest thing to do. So what else? So the other thing that we also did is looked at the economic impacts of this to see how much it would really cost us if we decided to do one approach over the other. So with that, we were able to see that the baseline, which was at $3.2 billion associated with the 2016 cost, the waste to energy approach was 12% more. So when you think about it though, 12% it's not that big of a number compared to, I don't know, let's say 50% more in your cost, but it still shows you that even at spending 12% more, you're not going to be reaching that 75% recycling rate. And then some of these scenarios show some type of cost savings. And the residential one, it's mainly because we're assuming some type of recycling revenue associated per ton. And we know nowadays that's probably not the same thing. So that might not be a negative number. The C&D though, we're not really assuming the revenue is associated with this, but it's from that large mass not going to a landfill. So you're getting that savings because you are no longer landfilling the C&D and yard trash that would have been landfilled. So that's where your cost savings are coming in for that -2%. But even then, you'll notice that no matter what you spend, you're probably going to be needing a comprehensive plan that takes into consideration multiple approaches. So the last thing that we wanted to do when it came to getting this 2016 profile are these environmental impacts. So we know that there is a specific composition associated with Florida's waste stream, and we also have a composition associated with the disposition, so the amount that's combusted, recycled, and landfilled. When we take these two together, we are able to use a life cycle assessment model, and one of the ones that is mostly used here in the US is the US EPA's waste reduction model, or WARN. So I provided you guys handouts earlier, and for those online who didn't get handouts, I will be providing you guys them later on, I promise, sorry. So the WARN model, this is kind of what it looks like for those of you online. Their handouts, this is a screenshot of some of the things. So the WARN model is a LCA tool. Its intentions are for those to simply be able to quantify their specific material and its management. So instead of going into the complexities associated with life cycle analysis, they just wanted users to be able to estimate or quantify their greenhouse gas emissions footprint or their energy footprint. So what I provided you guys is this table of the greenhouse gas emissions footprints. So you'll see that there are about 50 or so materials going down the column, and provided on the screen is for aluminum cans, aluminum ingot. And then for the rows, there's about 6 different types of management. So there's source reduction, recycled, landfilled, combusted, composted, and digested. For whenever you see these like parentheses or negative numbers, it's telling you that if you were to, for instance, recycle aluminum cans, then you are saving, for each ton of recycled aluminum cans, negative 152.76 million BTUs. For those of you guys here, you'll see that what you'll be looking at is the greenhouse gas emissions. So it would be a negative 9.11. So for each ton that you recycle aluminum cans, you're getting that much greenhouse gas avoided from being emitted because you're recycling it. The negative number is mainly because you're offsetting some type of virgin material or the use of it, versus things like landfilling where you're not really offsetting anything, you're just throwing it into the landfill, so you're getting emissions out of it. So that's where you see like 0.02 for aluminum cans. So using the WARN model and our composition and our disposition, we're able to estimate a footprint for 2016 on a per person scale. So the energy footprint was about negative 13,000 megajoules per person, and then the greenhouse gas footprint was negative 1.08 metric tons of CO2 equivalents per person. So what that actually means, because I know when you throw out numbers like megajoules and CO2, it's a little abstract. What it means is that we have 4.7 million vehicles taken off of the road for 1 year, and then there's 1.1 million garbage trucks of waste recycled instead of landfilled, and it's the energy to power 3.3 million homes for 1 year. So this gives you a metric for you to be able to understand what the greenhouse gas emissions for the whole 2016 really means in respect to Florida and Florida drivers or garbage truck owners or homes. So with the scenario though, how are we able to see how much of the recycling rate or the cost or the footprints compare to 2016? So far we've just been looking at it from a percentage, like this is how much percentage points the recycling rates increase or the percentage more cost associated with waste energy. So just kind of going into a different take on this, we wanted to set the number 1 as the equivalence to the 2016 total recycling rate, the total footprints for greenhouse gas and energy, and then the total cost. So for example, in 2016 we had a 59% recycling rate, then the waste to energy approach gave us a 69% recycling rate. So if we were to do 59 divided by 69%, we would see that there's a 1.24. So if 1 is our 2016 baseline, then we are 24% greater than that 2016 recycling rate. So with this in mind, what we did is we also did it for each environmental footprint and in each greenhouse gas, energy, and then the cost. So that blue line that you see going down 1, that is our 2016 recycling rate, our greenhouse gas emissions footprint, our energy use footprint, and our cost. I put that 24% up in red so you could see that's the number that we just calculated. But we also did the same thing for greenhouse gas emissions and energy use. So if the value is above the blue line, then you are getting a savings. So you're getting a savings in greenhouse gas emissions where the waste energy provides you a 12% more savings. So 12% more materials are offsetting whatever they are offsetting. And then a 26% savings in energy use. And then we did that also for the mixed waste approach and all the other approaches. What you'll notice is that the residential and the mixed waste recycling approaches have the biggest impact on greenhouse gas emissions savings. They both have 49% and 38% savings more than the baseline. And that's because we're recycling materials like newspapers and cardboard, aluminum cans, steel cans, and those materials have a very large impact on the environment because their virgin material extraction processes are so energy intensive or emission intensive. The two scenarios that didn't have as big of an impact or even a negative impact in some instances where they were releasing emissions are the C&D and yard trash recycling approach and the non-residential food waste composting approach. And that's because we're assuming that yard trash and food waste are being composted. And in warm, it makes this assumption that you're actually using energy, and that use of energy is not going to be saving you energy, but you do have a savings from the greenhouse gas emissions standpoint because one of the really big greenhouse gases is methane, and you are saving that because you are composting it. And your composting is offsetting any type of carbon storage. So you're able to store that carbon instead of release it. So with this in mind, we can see that even from a greenhouse gas and energy and total cost, there are some advantageousness when it comes to choosing one approach over the other. However, we did not decide that one would be the best versus another one, and that's simply because it depends on a community and what they think is most important. If they were to choose greenhouse gases or energy, then you would want to focus probably on the residential curbside recycling approach. But if your most important factor is cost and you want to have your costs reduced, you might want to still look at things like the residential curbside or the C&D and yard trash, because they still were able to provide you recycling rate increase, but not as a dramatic cost as waste to energy. So DEP released this executive summary, and this was back in 2017. And this was a comprehensive document that detailed a lot of the work that we did with DEP and with all of your discussions and feedback. And even with this, it was clear that reaching that 75% is still going to be very difficult. So from this motivated us to use this concept more so, this SMM idea. So for those of you who need a quick refresher on what SMM really means, because I know we just throw it out like you're supposed to know what it means, like sustainability. So SMM, as defined by the EPA, is provided up here, but I'm going to define it in my own words. So I would say sustainable materials management is about making the best decisions for your environment, for your society, and for your economy. You use different tools to be able to quantify the environmental, societal, or economic impacts, but the idea is that if you are going to recycle this material or decide to landfill this material, it's going to be based on those quantifiable impacts, with still the objective of reducing the use of materials and being able to use your resources more efficiently throughout their entire life cycle. So it's starting from your extraction to your processing, transportation, manufacturing, your usage stage, and then anything that happens end of life. So with SMM and this idea, we were able to focus in on one of the three most important pillars, which is the environment. And using life cycle models, we can quantify our environmental impact. And right now, what you saw before was the quantification through WARM, and that looks at just greenhouse gases and energy. So just a quick recap. I know everybody's probably seen these slides like somehow, somewhere. 1 ton of paper is not the same as 1 ton of aluminum cans in yard trash, but in a recycling rate where you're just taking a ton and you're putting it in your numerator and denominator, it means the same thing. It doesn't matter what the type of material is. You're just after something that is going to give you the biggest bump to your recycling rate. But when you're looking at things from an energy perspective, you know that a ton of aluminum cans is much more energy intensive than a ton of paper or a ton of yard trash. But how are you going to use something so abstract, such as greenhouse gases or energy, in goal setting? We're already so familiar with recycling rates. Making this big shift to something like greenhouse gases or energy might be too difficult to comprehend, more so because you can actually physically see maybe a recycling rate. So let's do a quick example. So if you had in 2008, this is our baseline year, a 75% recycling rate. So this 2008, this red bar has an associated composition, a disposition, and we're going to use WARM, and we're going to say, well, this 75% recycling rate, which has all those other things, it also has a -10 emissions footprint. So that's the same thing that we've done before, where we were able to use WARM to quantify and have this environmental footprint. So if we know that -10 is associated with that disposition and that composition, and we know that 75% is also associated with that disposition and composition, then we could say that they are basically equivalent to each other. 75% recycling, that mass-based recycling rate, is equivalent to -10 emissions footprint. So if you had another year, take for instance 2019, and this year had a 40% mass-based recycling rate, so it has its own disposition and composition, and we apply WARM, we could also get an environmental footprint of -6 metric ton CO2 equivalents per person. So using all of these numbers, how can we actually incorporate SMM and life cycle analysis into goal setting, where it's just as usable as a 75% recycling rate? So let's go through that. So we know these numbers, we just went through them. 75% mass-based recycling rate for the target year. So 2008, if I haven't said it already, is our target. We want to try and meet its recycling rate and its greenhouse gas emissions. And then our future year is what we're trying to measure compared to 2008 levels. So our greenhouse gas-based recycling rate, the first thing that we were going to do is we will divide our future rate emissions by our baseline rate emissions. This number will tell you how much of the future footprint has reached the baseline. So you're saying how much of that -6 has reached -10. And when you do that, you know it's just 60%, that simple 6 divided by 10 math. But the 60% is just comparing the emissions of 6 to 10. It's not comparing the actual 75% recycling rate. Because remember, we want to use that 75% as a comprehensive metric. We want to say that 75% is equal to not only a 75% recycling rate, but a 75% greenhouse gas recycling rate. So what we do is kind of correct it and multiply it by the target recycling rate, that 75%. When we multiply it, we're able to see how much that 60% is in reaching that 75%. And when we have that, we are able to see that we are at 45%. So using 75% and saying that it is 75% greenhouse gas-based recycling rate, then we are about 30% away from reaching that rate. That's what that 45% is telling you. But from a mass-based perspective, that 75%, we are about 35% away, because remember, we're at 40% right now. So now we have a comprehensive metric where we're able to say that 75% not only just signifies the mass-based impact, but it provides insight on your environmental progress and how close you are in reaching your greenhouse gas target. So just moving that 45% over here, you can begin to try and understand that negative 6% means that we are 45% away from reaching our 75% greenhouse gas recycling rate. So we went through this in detail with regarding to Florida. We looked at a example of Florida in 2008, and we came up with a few different types of baselines. I provided this handout to those here. For those of you online, I will provide this handout after the meeting, so please bear with me. Sorry about that. But basically, this paper that was published about a year or so ago really just details an example for Florida and how to use that concept that we just went over. How to be able to look at a greenhouse gas baseline, an energy baseline, and then also look at it from a greenhouse gas and energy recycling rate perspective. So expanding beyond just mass-based recycling rate. And then another thing that we just recently got accepted and hopefully published soon is this paper related to SMM and different types of approaches. So this paper I provided also as a draft for those attending, and I will provide it for you guys also online. And in here we discuss more approaches and examples to using SMM that go beyond just that recycling rate. There's more simpler, probably simpler is the only word that comes to mind right now, but I know that being able to translate things from a recycling rate to a greenhouse gas based recycling rate is not the most easiest or easiest concept to go through, and it might be quite dense. So what we did is stepped a little bit backwards and looked at SMM and different types of approaches where real policymakers could just, read this paper and be able to be inspired, hopefully, and gain from it some type of insight in their policy making. So with that in mind, Dr. Townsend will come up and discuss more so what our current project is, and then Carson will bring you guys up to speed in what we've been doing to WasteCalc.
Okay, good. So thank you, Malik. Don't go too far, though. Actually, I guess Carson's coming up in a second, right? Okay. So real quick, then, the idea is we did this first year project, and you know that 75% is not going to be reached in 2020. One of the comments that we got back, well, I guess a couple things motivating what we did next. One of them is that, great greenhouse gases. Some audiences we were kind of requested maybe put that a little further down the list to talk about energy. Other audiences we would talk about greenhouse gases as our example more often, but those were the two endpoints or environmental impact categories from WARM. But there's a lot of other ones out there too, right? I mean, one of the ones Karen used to bring up a lot is water, for example. Water use, Florida being a heavily water-dependent state. That's a critical issue with us. But if you look at life cycle assessment models, there's a ton of different types of impact categories out there, whether you're talking about ozone depletion or toxicity. And then we got feedback from a lot of folks in the working group about, well, what about jobs? Or what about, how much space it takes up in a landfill or things like that. So this new project is really focused on, number one, trying to develop more impact categories. In other words, to expand the toolbox beyond just greenhouse gas emissions and expand it beyond energy. But then the second thing is that's great, and we certainly always appreciate you guys listening to us talk about how to make these calculations, but how do you come up with some kind of tool or platform that can be used? So the proposal was really to say, hey, let's take all this stuff that we've been doing and put it into some kind of format, whether it be a model, an app, a spreadsheet that DEP could use, local governments could use, essentially anybody could use in the state of Florida. So that was really kind of our goal with respect to that. So to develop a tool, and then to develop these additional life cycle impact categories or factors beyond just energy and greenhouse gas emissions. One of the things that you'll hear Malik come up and talk about in a minute is all these different types of impact factors. We have to then develop those impact factors. Now, we're not in the business of going out there and collecting all the raw data. There are professors and scientists and government folks around the world who that is all they do. They collect these data categories. But as engineers, what we're trying to do is we're trying to take them, compile them into a more usable form. I think what's nice about WORM, if you ever had a chance to play around with it, it's pretty simple. It's ultimately, here's this one factor, you multiply it by a ton, and you get an output. Whereas to use some of the LCA models, and I'm not saying anything wrong with the LCA models, we're basically just taking those LCA models and trying to take a piece of it and simplify it and apply it. So one of the things, again, Malik will come and talk about is how to take that, that data that's out there and put it in a simple, usable form that then we could use as part of this task 3 to create this tool, okay? And then, of course, what we'll do is we'll take that tool and we'll try to evaluate some of those management practices. Where I'm going to transition over to Carson now is well, what is that tool going to look like? And so originally I was thinking, oh, maybe it would be like an app or something like that you have on your phone or on your computer. We made this big old spreadsheet as part of the work that Malik did the first year and all that stuff you've presented on. So we give you that spreadsheet. I don't know if that's the easiest kind of tool that's out there already. But then Karen and the department approached us about, hey, there's an existing, I'll call it a tool that's out there called WasteCalc. If you're not familiar with WasteCalc, it is used, and Carson will go over more details, it is used right now by local governments in the state of Florida. And the thought was, well, we'd like some assistance updating WasteCalc. And so the idea is, well, maybe we could use that as kind of a platform to integrate some of these sustainable materials management objectives into there. So I'm not saying, because that's the department's decision, not ours, I'm not saying that will ultimately be the case, but kind of what we've been doing lately is working with the department to update WasteCalc, but then kind of thinking long term that it's going to be a combination of what we're doing with that, what we're doing with the Hinkley Center, and what we're going to continue doing with the department and the Hinkley Center that I think might end up being the tool that will be available. So with that, what I wanted Carson to do is talk a little bit about WasteCalc, what she's been doing with it, how she helped the department with the rest of our team, and then talk a little bit about some of the research that she's involved with that relates to what's going on. So I think you'll get a kick out of that. So Carson, I'm going to hand it over to you.
Like he said, my name is Carson Klein, and I work with Dr. Townsend. And if I have a funny accent, it's because I'm from Kentucky. So please forgive me for that.
She's a gator now.
I am. Have my little gator bracelet on. So the first thing I want to talk about is WasteCalc. And what I've done first is taken a screenshot from a DEP report. And this has the total corrugated paper, recycled corrugated paper, office paper, yard trash. So what we do know, and every county that recycles knows, is the amount of, for example, corrugated paper that is recycled. But what we don't know is per commodity what is landfilled or combusted. So to figure this out, we use the tool WasteCalc. So like you said, WasteCalc is funded by DEP in around the 2000s. It's publicly available on websites. It's used by county solid waste and recycling coordinators to estimate the county's total MSW composition. Like we said, the material composition, recycled, combusted, landfilled. And it provides each county data for their own purposes, but it also provides the state data on how they can implement more policy. So I'm going to start with this graphic. It's very it's conceptual of how WasteCalc works. So the input is a series of 18 commodities that DEP recognizes. And so you would enter those recycled tons, and then you have your total amount of landfill tons and combusted tons. So you enter those in, real simple, click submit, and it goes through some behind the scenes calculations where you have US EPA data, which is national data, and we incorporate a lot of Florida waste composition data to normalize the national data to not only statewide data, but county specific data. And for the original waste composition, if you guys don't know what waste composition studies are, we go to a transfer station or a landfill, the truck dumps the garbage and we sort it. So we figure out what's in it. But these counties in blue were the ones that were used for the original development of WasteCalc. So you can see There's probably 10 or 11 there, but they were used as baselines with many assumptions to calculate for other counties. And the output for WasteCalc is percent MSW composition. But with this, it hasn't been updated in about 20 years. And DEP came to us and said, hey, figure out how this works. You know, what's going on? How can we update it and make it more reflective of the current waste stream? So that's what we did. For the input category, they're all the same with the recycled tons, landfill done, combusted tons, but we've also entered a section for collected C&D tons because this is more closely tracked by the state, and having that available data makes it easier, helps with a better estimate of MSW composition. We've also taken the US EPA data and updated it to the most recent publishing, as well as collected Florida waste composition studies. And you can see these are the counties that we are currently using for the WasteCalc data. And then the output is very similar. What has percent MSW composition, but it also puts it out in tons of MSW composition. And that helps with solid waste and county coordinators filling out reports so they don't have to do all that manually. So what's next with waste composition data? So I've highlighted, the orange again is the counties that we've collected for the updated WasteCalc, and I've highlighted in green some areas where we have gaps. But what we've been working on this summer with DEP is collecting more data. So I actually have a bunch of peers who have spent the past month out in garbage, and I will be joining them this week, as well as some DEP folks will be there. And by the end of the summer, we plan to have we will have data on all the counties highlighted in red. So that can easily be incorporated into WasteCalc to have more, accurate estimates. So along with waste composition data, this is pictures of us in our glorious job digging through the garbage, right? And so it is what it looks like. They take the garbage, they dump it on a table, and we have all of these buckets where we sort materials. We take those materials, and it's on a weight basis, so we sort them, we weigh it. But one thing I've been working on is looking at generator types and how, I guess if there's a correlation between sociodemographic factors and waste disposal. So I focused on single family residential, so anything that's, curbside, be picked up from your home. And we sorted not only the garbage, but also the recyclables. So that way we can look at, cycling rates along with that. But today I wanted to show you guys the results from the waste and the recyclables in relation to median household income.
How'd you come up with the route?
So we came up with the routes by, we were able to get hauler maps. And so what we did is we took all the garbage routes and all the recycling routes, and we basically had to overlay them, see which ones overlapped, because we wanted to make sure that the garbage we recycled, or the garbage we sorted, was the same from the same area of the recyclables we sorted. So we had about 18 that overlapped, and I first looked at income to decide what would be like a high, average, and low demographic, just because I needed to decide which routes I should pick. I didn't want to just sample and they all be from one demographic. So we took the overlap, we have the routes, and we had someone in the nice AC in the transfer station being like, yeah, we need that truck, so it would come and dump where we need it. And so we knew exactly where it was coming from. So that helps a lot in the analysis. So this is the result from the recyclables. And one of the main things here is you can see from the fibers content decreases and the containers increase from low to high income. And I would say, fibers are your paper. So it's your cardboard, your newspaper, and then your fibers are your plastic cans, aluminum cans, steel cans, and glass. But we noticed as we were sorting the high income recyclables, there was significantly more glass, and glass is really heavy. So that would contribute to the weight difference. But one thing interesting is we looked at contamination. So we sorted fibers separate from containers. And so we looked at what fibers came in the containers, because that stuff ends up being trash, and what containers came in the fibers. And interestingly enough, it ended up being, 1 to 3% throughout all the demographics. So that was pretty interesting to see that contamination really isn't as much as an issue maybe in this area, what we're looking at, than a lot of other places.
This is composition of recycling. You will also at some point have the actual recycling rate
Correct.
for the different areas. We're still waiting on getting all the numbers back on that.
Yeah, we'll have recycling rates, and we can relate all of this to recycling participation. We've been out, getting how many on these routes, how many people lay out their recycling bins and who don't. So we'll be able to look at contamination, recycling rates, participation, all of that in relation to composition, obviously, because we sorted the composition in relation to socio-demographic factors.
Is this dual stream data? Is that what we're looking at? Dual stream recycling data?
Yes. Yeah.
This is Alachua?
This is Alachua. Yeah.
Okay.
Sorry.
Wait a second. We've been on this truck. That's why we were all shocked. Just a funny thing though, I always would think the high medium household would have a larger fibers because they're online shoppers.
Okay.
And so, that would show me that they would have more boxes and that they would be getting rid of. But
And-
it's funny that it's the low end's got the higher rate.
Well, that could definitely be true. We did notice a lot more online shopping containers, but they don't weigh as much as, say, the glass. That's also being weighed. So that we do have data specific on, these are all broken up into a bunch of categories. So we have cardboard, newspaper, glass, aluminum cans, we have it all. This is just a summary. We have it all broken up real specifically so we can compare cardboard boxes from low income to high income, and, so we'll be able to do that.
If you add all the pies besides the orange and the blue, what does that add to, like 15%? That's pretty typical. I know things you can see higher than that, but it's not like contamination. It's like, it's not as pristine because it's a dual stream. It's better, but the total magnitude is going on around.
Were you looking at the tons generated per capita, like per household?
Yeah, so I have the route data. So I guess the idea would look on this as a per household, the results would be in a per household data. But just recently I haven't been able to sit down and crunch all the numbers yet. But I do have every truck route and how many tons they brought in for every route that we looked at for the past year.
So this is looking at the composition from the different sectors that you looked at. It's not necessarily looking at how much recyclables or waste is generated by the household.
Correct. This is just composition. Yeah.
But that data is coming.
It is
Yeah,
coming.
so that, if you start looking at it that way, your composition might change because there might
Sure.
be more consumption from the higher household versus the other, which could skew it because they're buying other things. Just throwing it out.
Yeah. Our data is slowly coming in, so I'll be able to get into all that real soon. I'm excited to not be in the garbage and look at these numbers. Does anyone else have any questions on recyclables?
Was this just the current audit that you did?
I don't know how this works.
Okay, just repeat the question so that when you're answering the questions, Carson, they know people online can hear what the question is. They can't hear the people in the audience ask the questions.
Oh, okay. Sorry.
Maybe that for that last one, just repeat what Travis just asked about.
Travis just asked if this was total generated composition, and it's not because we haven't applied the total tonnages throughout the past year for each route yet. But that data is coming, and we're gonna look at that real soon. But he was mentioning, low versus high. One might have higher generation than the other, which could obviously skew these results a bit. But this is just focusing on composition for the routes that we sampled.
And I will say one thing, if you look at the other category plus trash plus non-recyclable, what is the other?
Other is what fell through our screen. So our table, we
Those
have,
are things that would be out throws at a MRF.
yeah,
They're going to be small.
too small for them to sort.
If you add up other plus trash plus non-recyclables, that's 18% for low. And then it's other plus trash plus non-recyclables, it's like, what, 14%. I don't know how the statistics will fall out, but I mean, at least just comparing those two, there's some potential trend.
Yeah, I think
for contamination.
This is very, baseline for the beginning of the study, but I'm glad you guys are interested because that makes me more excited too to get in and give y'all some answers.
There's like a little seal on there.
This is the composition for solid waste. So this is the straight garbage, right? Paper was pretty similar. Plastics, something very interesting that we noticed is that the organics for the low income and the high income were pretty similar, 40 and 41%, while the average is around 29. So there's not too big of a difference in the composition. And again, we sorted solid waste into 60 some categories of garbage. So this again is just a big overview. All of these will break up into a ton. But focusing on organics, because low income and high income are within 1%, you can see here that 75% from low income was food waste, where 56 of that for high income was food waste. So it's evident here in our study going from low income to high incomes that the food waste does decrease, but the animal byproduct increases. So, but it was really evident. We got to a point where the garbage would be dumped on our table, and we were like, "This is low income because of all the food." I mean, we knew just looking at it, which is kind of crazy. You can look at garbage and figure out where it came from, Does anyone have any questions on these numbers? Yep, okay. So again, there's a couple more pictures, and I'll invite Malak back up here to talk about some more tools. Thank you, guys. Thank you, Carson. Interesting relationships between low and high income. You have a question, Carson, from David Gregory. And I will read it out loud once I find it. Okay. How many samples each from the low, average, and high demographic groups?
We did 5 recyclables and 5 solid waste from each demographic because there were only 18 that overlapped, and so getting 15 out of that 18 was a good goal.
So 5 from low and 5 from high and 5 from medium.
Correct.
Yeah. And those are samples of truckloads, right?
Of what?
Truckloads, like 5?
Yes.
Yeah.
15 recyclables and 15 garbage.
So 15 recyclables, 15 garbage. Hopefully that answers your question. All right. So we are going to continue with our lovely conversation related to this new Hinkley Center project that we've been working on nice and hard since October. So you now have an idea of what WasteCalc is. And then something that Dr. Townsend mentioned earlier was that massive spreadsheet that we put together as part of the first project. And both of these in conjunction will be able to tell a county or a county recycling coordinator how much of each of their materials are either collected, landfilled, combusted, recycled, or composted. So with that in mind, how are we able to take a mass of a material and then quantify its environmental impacts and footprints? We already went over WARM, and WARM, as you guys saw from those tables, provides you these things called greenhouse gas and energy factors. We just translated them to life cycle impact factors. That's what the LCI stands for. So that is obtained from LCA models. But there are still some other types of LCI factors that haven't been obtained, and that's what we kind of want to talk about in this next portion of the presentation. But before we could go into the details of what an LCI factor is, it's good to understand what an LCA model does and how it really quantifies these factors in the first place. So typically, most LCA models will look at different portions or phases of a material, starting with raw material extraction. So let's take, for example, HDPE. HDPE, you're going to be extracting the petroleum, and then from there you're going to be processing it. You're processing the material, and then once you process that petroleum, you can then create a material out of its manufacturing. So it's going from petroleum to maybe HDPE pellets. So these pellets are your materials. And then from there, you want to transform these materials into an actual product. So if we're into HDPE bottles, those pellets are then going to be transformed into an HDPE bottle during product manufacturing. Then there's that distribution and transportation. All of those T's that you see up there just stand for transportation. And in the in-use, a lot of the times it's just related to being able to transport, distribute the HDPE bottles, and then somebody going in and consuming them. And then the end-of-life management is what we've been focusing on. So WARM right now only looks at things from an end-of-life perspective. So these waste management footprints that you're getting are really just specific to it being recycled or landfilled or combusted. It doesn't really consider all of these other upstream activities or life cycle stages. However, if you're taking into consideration source reduction or recycling, you are taking that material and you're putting it back into the life stage. So you're putting it back into product manufacturing. So it will take into consideration to some extent some of these upstream stages. But when you think of things like landfilling or combustion, it's typically only focusing on that orange end of life box. So each one of these life stages has a material or an energy that's inputted, and then there's also a waste or emissions that's exported out. So those are your outputs. What an LCA model does is it'll just look at every single one of those materials and energy, emissions, and waste associated with each stage, and then be able to quantify it and translate it to impacts into things like global warming potential or energy use. So what WARM does, it makes things a little bit easier. Instead of going into the details of materials and energy and emissions, it'll simplify things and just do these things in a greenhouse gas or an energy factor. So that's when you have a mass of a material and then its associated greenhouse gas emissions. So you'll see there's CO2, methane, and nitrogen oxide, and that's because those are the most persistent, or not persistent, but majorly impacting towards the greenhouse gas emissions of materials. So it'll convert it then to a comparable unit, which are CO2 equivalents, and then we can create an LCI factor for global warming from that. So that's what WARM's already been doing. It's been taking all of these emissions that you get from the waste and from the materials being inputted and from the energy being inputted, and it'll quantify it in terms of a ton. So we want to do something similar to that. So as Dr. Townsend mentioned, one of the objectives is to not only create this spreadsheet or this workbook or whatever form our final tool will be in, but to create LCI factors for things that aren't in existence right now. WARM provides things for global warming and energy, but there's other environmental impacts that we believe would be very insightful in use with specific Florida audiences. And those are things like acidification, eutrophication, human toxicity, ecotoxicity, water depletion, landfill space savings. And then there's also some things that aren't necessarily environmental, but they're still part of this idea of SMM, which is taking into consideration the economics and the societal impacts. So we focused on jobs produced for societal impacts, and then for economics, total cost and recyclability. Recyclability could be defined something as maybe like commodity pricing. And then while we have all of these impact factors, in order for us to decide what our objective metric would be, that's going to be up to the community. And it might be up to us and the stakeholder working group to decide maybe one impact factor versus the other as a starting ground before maybe releasing or using all of them at the same time. So I'm just going to go into depth so you guys can have a better understanding, because I know when you say acidification, it doesn't really mean anything. Like, you know, it's not good for the environment, but why and what is it measuring? So we'll start with global warming potential. So that is just the greenhouse gas emissions. The main ones that are taken into consideration are CO2, methane, and nitrogen oxides. So greenhouse gases, what they do, they absorb the energy from the earth and they don't let it escape into space. So it'll slow that type of reaction from happening. And when that happens, you have a large amount of ecosystems impacted, which you probably already know since people like to focus on climate change. There's too many documentaries to list probably. But anyways, so what we did is we just used the global warming potential and decided that that is one of our important environmental impacts since it has such large environmental impacts on the ecosystems. So then the next one is related to energy use. So this would be expressed in units of megajoules, and it's related to the energy that's used both directly and indirectly in any type of life stage or producing a product or a material, the transportation, and it includes both renewable and non-renewable energies. The third one that we're looking at is this acidification potential, and that's just the amount of acids that are really being, emitted or in the ecosystem. And the main reason why you care about acidification potential is because if it's entering into your lakes or rivers or even your buildings, it's causing damage. It's causing damage to those ecosystems, to those wildlife, and then it also causes damages to your buildings, and we clearly don't want that. So these units are expressed in kilograms of sulfur dioxide, and like CO2 or the global warming potential, it's an equivalent. So they'll take into consideration other emissions that aren't just sulfur dioxide. So it'd be like nitrogen oxide, hydrogen fluoride, and then the other two. And then it really just measures how much each of these materials, when they're released as air emissions, and their impact onto different types of ecosystems or the water or the air. So then we look at eutrophication potential, and this one might be a little bit more closer to home with respect to Florida. It's a measurement of how much phosphates and nitrates are really in our water bodies. So we know that having those types of emissions or materials or substances actually have detrimental impacts on the wildlife and aquatic wildlife. So that is one of the main reasons that we decided to include this, especially since it's very relevant to Florida's ecosystem. So these are also expressed in equivalent units. There's actually a few different types of units that could be expressed related to eutrophication. We chose the kilogram nitrogen equivalents as our main measurement, and those also include other types of kilograms of substances that are important. And this is a measure of the nutrients or the emissions to both water and air. So acidification was just the emissions to air. This one would be related to water and air. So then there's human toxicity potential, and I think it's pretty obvious because we don't want people to get diseases or cancer. And the units here, though, are expressed in CTUH, which are interpreted as disease cases per kilogram of substances. And this is related to emissions not just to air or water, but it's air, soil, water, sometimes even food. And then something similar to human toxicity are things related to aquatic ecotoxicity. And these are in kind of similar units. Instead of CTUH, it's CTUE, and that's interpreted as the potentially affected fraction of species over time and volume per kilogram of substance emitted. And this is also to the different phases that are air, water, soils, and it impacts specifically the aquatic ecosystems. And then the last one, which I think everyone's probably most excited about, is water depletion. So this is the ideal where if you are using water in a way that it is evaporated or incorporated, where it's no longer in its original form or it's transformed from other watersheds or even dispersed of in the sea, then it's considered consumed or used and no longer available as it originally was. And in that case, then you are depleting water. And they're typically expressed in units of like meters cubed per water, but we'll express them in gallons since they're more easier to conceptually understand or physically understand. So the ones that we just talked about, these are environmental impacts that are able to be quantifiable through a traditional LCA model. So things like warm, that would be considered somewhat of a traditional LCA model. And what we're going to do is just talk about more LCA models and how we could obtain the other LCA factors beyond greenhouse gases and warm. So the four that we've been working with are the waste reduction model, and then there's municipal solid waste decision support tool, so that's MSW-DST, solid waste optimization life cycle framework, SWIF, and then environmental assessment systems for environmental technologies, EASTEC. So just going more in depth so you guys have a better understanding of maybe like where they originated from, their main capabilities, the types of impact factors that they include, and how we can use them to obtain our other LCI factors. So WARM is specific audience is the US, and it was developed by the US EPA. It is a Excel workbook or a desktop application that you can download. It's dependent on a mass of material that you input, and then the management that they include is source reduction, landfilled, composted, combusted, recycled, anaerobic digested. And then it looks at only two impact categories. That's global warming potential, so the greenhouse gases, and then energy use. WARM does not directly say why they decided not to include other impact categories, but if I had to assume, it'd be because greenhouse gases and energy are one of the most widely documented or widely available documented impact factors. So the other US-specific LCA model is MSW-DST, and it is actually run as a desktop application. It's not available as an Excel spreadsheet like WARM, and it doesn't provide things nicely into an impact factor. It's actually a little bit more work for you to get something out of it, but you can still use it on the same basis as putting in a massive material, and then it's available. Managements are less than WARM. There's landfilled, combusted, recycled, and composted, but it does include more impact categories. So it'll include acidification potential, eutrophication potential, human toxicity, and ecotoxicity. It doesn't include energy though. The third one that is also geared to a US audience was developed by NC State, and this is also in the form of a workbook or so. It's not a desktop application, and it also focuses on an input of mass of a material. It's not in the same type of format as WARM as you see in those tables. You also have to work with it in order to get what you need out of it, but it provides a good amount of management practices, so landfilled, combusted, recycled, composted, and then even anaerobic digested. And this one actually includes almost all of the impact categories that we would like to obtain from it. So global warming, energy, acidification, eutrophication, human, ecotoxicity, and then even water depletion. And then the last one, this one is the most different one because it is specific to a Europe audience, and it was developed by the Technical University of Denmark. So this is a desktop application similar to MSW-DST. It's not provided in an Excel spreadsheet. It definitely doesn't have those nice tables that you see from WARM, but you could still work with it to also get what you need. And it also has almost nearly the same management and the impact categories as SWIF, which was that US-based one. So now that you have a better understanding of these four different types of models, we're going to go through an example of how these four different models calculate global warming potential for both aluminum cans and then PET bottles. But we'll start with aluminum cans so that you have a good example or baseline to see how HGEP is calculated, PET. So going back to our lovely, colorful life cycle, we need to An LCA needs to include the emissions or the energy, the material, the waste associated with each one of these processes. So there's the raw material extraction all the way to end of life. So going through this with an example of aluminum cans and using SWOF, which is that US-based one that provided nearly all the LCI factors of interest and a decent amount of management practices. So a virgin material. So aluminum cans start off as aluminum ingot, and they are extracted and then transported. Then they're processed into whatever they need to be processed to, and transported so that they can be material processed to probably things like an aluminum sheet or so. And then once you have that, you will transport them once again and then make a product out of them. So those those aluminum cans will then be produced out of those aluminum sheets. And then from there, you'll also transport them and distribute them so they can be used. And then once they're used, they are considered end-of-life managed. If you're going to recycle them, that's awesome, because you should. If you don't, it sucks. But recycling then also has a certain amount of material that will not necessarily be completely sent to a remanufacturer. There is a residual amount, which we're all familiar with, and that is also included as part of our end-of-life management. But if you're recycling them, then you're assuming they're going to be remanufactured into new aluminum cans. So they're going to be offsetting or basically no longer requiring you to use virgin material. So this whole process will give you a aluminum can factor. So in warm, we already saw what that was for aluminum cans, but in SWOF, this number is negative 15.7. So once you recycle an aluminum can according to SWOF, then you have an offset of negative 15.7 metric ton CO2. But how they actually get this number, we have never really dived into. So I want to take this chance so you guys can get a better understanding of why these numbers are being used and where they really come from. So each one of these processes will have a metric ton CO2 equivalent associated per ton of a material. This would be associated with a ton of virgin material, and then the end of life would be associated with a ton of secondary material or that recycled material. Now, it's not as easy as summing up all of these materials to get that negative 15.7, even though that's probably your intuition. Just sum them all up and then you'll get negative 15.7. Instead, what they do is they'll focus on this idea where you look at the emissions associated with using a virgin material all the way through to product manufacture, and then versus using a remanufactured material to product manufacture. So again, we're looking at the difference between virgin material use in product manufacture versus recycled material use in product manufacture. So when you take that into consideration, you take the virgin materials used in that product manufacture, and then those emissions are typically much larger because you're using virgin material, and then you subtract it from the recycled material. So you get this negative number in the end, even though when you do add the emissions associated with sorting and processing, the emissions associated with transportation, and then even the emissions associated with landfilling, you still have a negative number because the virgin material number, that first one, is so much larger than everything else, hence the negative 15.7. So WARM does some similar things, and so do so does MSWDST. They both look at things from a perspective of taking the virgin and subtracting it from the secondary material or that recycled material. But not all of the LCA models will do that. There's differences in how they assume these numbers and in the methods that they do to create these numbers. So keeping that in mind, we're going to continue this example with aluminum cans, where you see that negative 15.7 is associated with SWOF. The first thing that I want you guys to look at then is WARM. So WARM is at negative 9.11 number. So if you look at your sheet again and you look at recycled greenhouse gas emissions associated with aluminum cans, you see that column, you'll see that it's that negative 9.11 number. And then you'll compare it with MSW DST, and that's a negative 0.42. And then looking at East Tech, it's negative 8.37. So I would say that SWF, MSW DST, and WARM all use the same assumption of doing a virgin minus a secondary material. And it kind of explains how you see WARM and DST in the same realm. SWF, though, has a much larger, I guess, impact savings in greenhouse gases than the other ones. And I would say that's because it's including or assuming maybe a bigger offset associated with their virgin materials. So there might be a difference, or there's definitely a difference in whatever assumptions they're using to estimate their virgin material instead of their secondary. But it looks like DST and WARM are using similar assumptions, hence their similarities. East Tech has the least amount, and that's because they're not really using that idea of secondary minus virgin. They're just assuming a certain amount is used in the production. And you'll see that their assumptions does make a difference when we also look at it in consideration in PET in the next slide. But before we move on, I wanted to highlight this blue bar. The blue bar represents that remanufacturing number. And like we saw earlier, that's that virgin number. You know, no matter how big how big or small the secondary number is, it really matters what your virgin material is. So in aluminum cans, the use of virgin material is a lot more environmentally impactful than recycling it, which means that if you are going to decide to buy an aluminum can instead of a glass bottle, you would definitely want to make sure you recycle aluminum can so you can offset all these emissions. But if you buy a glass can instead, it might not be that environmentally terrible if you decided to throw it away. So looking at this also with PET bottles, SWF, DST, and WARM also have kind of a similar realm or magnitude of the numbers, but East Tech has a much different number. And I will be honest, I am not entirely sure why that one is so different as compared to the other ones. I would say my next task would be to really focus in and try to understand better how these assumptions are being used in East Tech and why they are being used versus these other three models that are using similar ones. And those other three ones are US based, so maybe there's a difference between US and European assumptions. Again, though, when you see the blue bars, you note that the remanufacturing is really what matters, even though like emissions from the MRF are still very much important. So just a quick comparison. So before we go through a quick comparison of PET and aluminum cans, I wanted to show you guys an example of how the water depletion factors are also created. So we're already looked at the global warming ones, and now we're going to spend some time on water depletion. So similarly, each process has a gallon per ton associated with its material or its life stage. So there's the raw material extraction, the processing, material manufacturing, product use, end-of-life treatment, and then your manufacturing. So with aluminum cans, every single time that you recycle an aluminum can, for that ton, you get negative 0.24 gallons. So about a quarter gallon of water is saved each time you recycle a ton of aluminum cans. What we know, or what we've done so far, is use a traditional LCA model, SWF, to be able to quantify each one of these LCA impact factors, and then create these LCI factors for aluminum and PET. So what you'll see here are the numbers associated with each one of these impact factors. So for 8 aluminum cans and then for a ton of PET. In almost all of these instances, the aluminum cans have a much greater offset than the plastic. The one that the plastic had a more offset was with eutrophication, where it was negative 2.4 and aluminum cans was negative 1.4. I would assume it's because they'd be requiring more release of nitrates or phosphates during the extraction process of petroleum maybe. I'll be also honest, it might not be necessarily that. It could be related to the fact that recycling it doesn't really offset as much when it comes to aluminum cans. So essentially what we did here is show you guys a sneak peek of what we have in mind for all the other materials and all their other managements. So with this in mind, we could see that, all right, aluminum cans, if I really wanted to go after them and have them prioritized as my recycling rate, I would say that even if it was global warming or ecotoxicity or water depletion, it shows you that 1 ton of it has a large environmental impact. And it continues with this idea of SMM, where you should be making your decisions based on the environmental impact, the economic, and the social. So, but the one thing that we would like to also demonstrate here is how we can use those numbers that you just saw that are still pretty abstract in policy or in goal setting. And what we did is we came up with a scenario for Florida. So these are using Florida's numbers. So we set up a hypothetical 2008, similar to what we did in that paper. And in 2008, there was a recycling rate, we'll say it's 75%. So that's in the spirit of that 75% by 2020. And 2008 was the year when the legislation was passed. And for the whole materials waste stream and all of its dispositions, so the amount of each material combusted, recycled, landfilled, all of those numbers net, we still ended up getting a negative 0.3 gallons per person. Versus in 2017, we did the same thing. And in 2017, you'll notice that the recycling rate is 52%. And in 2016, we showed you a recycling rate of 56%. I just want to note that that is mainly not because we're recycling less, but because of different types of accounting that we are doing now according to our landfill standards and our recycled numbers. And with that in mind, we could see that our water depletion footprint is negative 0.02 gallons per person. So taking these numbers and kind of what we did before, where we took the hypothetical situation of 75% in 2008 and that 2019 number with the 45%, we'll do the same thing here, but with water depletion. So we know that in 2008, there was a 75% recycling rate. Then we know that we calculated that water depletion, so it was the gallons per person. And then we said that they were equivalent to one another. And then we have also a 52% recycling rate in 2017. There's that negative 0.02 number again. And then we still want to see how can we actually use this number and say that that 75% is not only equivalent to a mass-based recycling rate, but also the negative 0.03 gallons per person. So using the idea or that equation before, instead of a greenhouse gas-based recycling rate, it's a water depletion-based recycling rate, where it's the future year water depletion footprint divided by the baseline year water depletion footprint, and then multiplied by that 75% target to give us a 52%. So the next thing that we wanted to look at with regards to environmental savings is this idea of landfill space savings. So Carson's going to be coming back up here, and she will be able to provide you greater insight on how we will go about doing that.
Did y'all miss me? So I'm back. Okay, so part of my thesis, one of the things we were looking at is, do different materials contribute to landfill volume? And the idea behind this is, if you have 1 ton of paper, 1 ton of plastic, 1 ton of aluminum, and you threw them into a landfill, they got compacted, they would take up different amounts of space, right? So we're going to do this using density, and this is our Tobanometer, and Tobin is sitting right over there if he wants to wave to everybody. This was him in 2004, that's what it says. But this machine is designed to compress materials. So the idea is that we do these waste comp sorts, and so I have trash bags full of sorted garbage ready for us to squish, and we'll weigh the material, we'll put it in this machine, and we'll start compressing it at different starting at like 2,000 pounds down to like a full landfill pressure, because, depending on where you are in the landfill, it would be experiencing different force of pressure. So the idea is to take all these materials, find their densities, and apply them again. So we'll have 1 ton of paper, 1 ton of plastic, 1 ton of aluminum, but you could see that 1 ton of plastic could contribute to 20 cubic yards of plastic. Now, these aren't real numbers, these aren't set numbers, but the idea is to be able to have a landfill space savings per material, like per ton. So, and then we could also look at cost savings when compared to combusting or recycling materials. So this was actually pretty straightforward in explaining, we have these materials, find the densities, apply that, and we could estimate landfill space savings. We could apply them to WasteCalc studies and figure out how much landfill space a certain county or a certain area or even the state is filling up. And you could also predict the lifespan of a landfill. If materials continue to, the composition stays the same, you could estimate how long that landfill has left. So, that's really all I have to say about this topic. Like I said, it's pretty straightforward, and invite Malak back up here.
Thank you, Carson. So the remaining impact categories we are starting or focusing on in our next steps for this project. And they are the jobs produced, the total cost, and the recyclability. So at this point, we kind of want to open up the floor for a discussion on methods to go about getting these numbers, especially things related to maybe the definition of what recyclability could mean. It doesn't necessarily have to abide to just commodity pricing. And then there's also things like jobs produced and total cost that I believe that we could use some of the valuable information that you as a stakeholder would be able to provide to us related to industry data or just data related to the county that would be helpful related to gathering these numbers to be Florida specific.
I'll tell you what, so here's what we want you to thought on. We don't need it right now, but just these other factors. What I want to do is that we've got a little bit more, and I want to make sure that we cover everything in time because we've got another student coming in. So the project that we're presenting on specifically today, basically it's continuing what we were doing before. We were looking at updating these emissions factors, which that's a huge amount of work and effort to try to do. You're seeing the first glimpse of that, and we'll be producing that throughout the summer and then or in the falls when we have that report. I think they can hear me okay. The second thing would be that the tool, we continue to work with the tool, we continue to work with DEP on that. So this next year, however, I think one of the things that we really wanted to focus on heavily, and I'm going to hurry so I get to Beatrice's thing, is source reduction. I think one of the big things we learned all along is that when you start really looking at making an impact, there's not much more you can do than stop making waste or to reuse materials or to make things last longer. So the project that we're going to be presenting to and proposing on this Wednesday in front of the Hinkley Center's Research Selection Committee is really about continuing this work, working with the department, working with local government, working with the stakeholders to evolve this SMM tool that hopefully could be used in future discussions with the legislature, whoever. But the idea is a big component of that is going to be source reduction. And what I want to do is I'm going to bring up Beatrice because she's doing 2 different projects. And I really want you to hear briefly about, before everybody needs to hit the road, that regard to this upstream materials issue. So Beatrice, take it away.
Good afternoon. So I am a master's student of Dr. Townsend, and my thesis involves the impacts of consumption and the benefits of source reduction. So my first question that I wanted to answer on my thesis is, how do we include upstream impacts in decision making? So for example, if we have an aluminum can and a glass bottle, we might decide to buy an aluminum can because we know it's more likely to get recycled than a glass bottle, and because we know the benefits of recycling the aluminum can, it's bigger than the benefits of recycling the glass bottle. But what are the impacts of those materials being produced in the first place? So that's what I wanted to address. So just let's focus on life cycle. So life cycle involves downstream and upstream. Right now, we are talking about downstream. Downstream is the end of life. It's what happens to the materials after they become waste. So Malak was talking about, we're focusing on recycling rates, trying to improve recycling rates. Upstream is everything that happens before the material becomes waste. So all the manufacturing process and everything. And so the life cycle involves both upstream and downstream. And what I wanted to do as part of my thesis was to quantify those upstream and downstream impacts or footprints. So we applied to do that, we apply Alachua County's waste management numbers, and we came up with a methodology to measure those upstream and downstream footprints. So how did we do it? First of all, we gathered warm factors and the masses of the management of each of those materials. So the warm factors, I think Malak told us a lot about it, so I don't have to go into detail on that. But the source reduction factor includes the upstream impacts, right? Everything that we are avoiding upstream because we're not consuming that material, right? But in the upstream, we wanted to measure the impacts of consumption. So what we did was to use the source reduction factor, but change the sign. Instead of negative, instead of being a benefit of avoided emissions, is what it is. It is generated, the emissions generated through the consumption. So we just switch the signs from negative to positive. And then we multiply that by the consumed amounts of each material. The only problem is we don't track the consumption of products. So we had to come up with a lot of assumptions, and I'm gonna go through them really quick because it's a lot of assumptions. But we did assumptions for non-durable goods, which are materials that are discarded within a short period of time, for example, aluminum cans and glass bottles. So because they have a short lifespan, we consider that everything that is collected is generated also in the same year because of this short lifespan. Now for durable goods are materials such as furniture, major appliances, small appliances, materials that are supposed to last years or even decades. For that, we had to go through sales data that were available. And for construction and demolition materials, we used an EPA methodology, and we apply the Alachua County population numbers to those numbers to get information. So that's how we calculated the upstream or the impacts of consumption. Downstream is much easier. We just apply the mass that is recycled times the recycling factor and the mass that is disposed by the landfilling factor, the mass that is combusted by the combustion factor. And these are some of the results we got. Of course, there's a lot more materials than this, but let's focus on this right now. So what does it mean? If we look at the orange bars are the downstream savings, the waste management savings, what we achieved by recycling those materials. So for example, the big orange bar relates to corrugated paper. So by recycling 59% of corrugated paper, that's how much greenhouse gas emissions we are avoiding, right? So for the other materials, you can barely see the orange bar. That might mean, for example, for other plastics, that might mean that our recycling rates are too low. Or for concrete, our recycling is 81%, but we can barely see any avoided impacts. That could mean maybe that we are not doing a good job on the reuse of this recycled concrete because you're not avoiding any more, let's say, cement of being mined or something like that. And then the blue bars are the upstream impacts. Everything that is, all the greenhouse gas emissions that are generated upstream. So let's go back to corrugated paper. The blue bar means that in order to produce or to manufacture all the corrugated paper consumed in Alachua County, that's how much greenhouse gas emissions were generated in the process. Okay, so what does that mean? Well, it means that we probably should be focusing on beyond recycling. So as local governments, maybe we should be incentivizing reuse, or we should be incentivizing donation of materials. As citizens, we could be buying less stuff, fixing our broken products, making our products last longer. So the conclusion is we should be consuming less. And this conclusion led me to another question that I'm also addressing as part of my thesis. How much environmental benefits can be achieved with source reduction? And for my thesis, I used durable goods as my materials. So durable goods, I'm including right now, this is a work in progress, but I'm including major appliances, small appliances, electronics, and furniture. So last year, I had the opportunity to spend a lot of time in the transfer station floor as part of a project we were working on with Alachua County. And they wanted to see if, they wanted to evaluate the possibility of creating maybe a reuse facility for these durable goods that could be reused. And so sometimes you hear stories of loads of trucks that come from school districts with nothing but chairs or nothing but desks. So what I wanted to do is measure what benefits could be achieved through reusing these materials. So what if we started looking at our waste management differently? What if instead of just putting out every week our waste, our recyclables, and our yard waste, which is what we put out in Alachua County, we also put out every week durable goods. And then a truck would come, pick up our durable goods, let's say a broken toaster or something that we didn't want anymore, or a vacuum cleaner. And they would take it to this reuse facility, and other residents could go and get these materials for free. So this is what I wanted to measure. And I also wanted to compare it to something that is done in a lot of places, which is the collection and composting of food waste. And so again, to measure that, I used Alachua County's mass data and recovery rates. So for recyclables and yard waste, I used the recovery rates for Alachua County. For durable goods, I consider that only 10% of all the durable goods that are produced are recovered and sent to this reuse facility, so they are source reduced. For food waste, I consider that 50%, which is a lot, of food waste that is produced is collected separately and composted. And I also wanted to look at costs associated with the treatment of each of these materials. So the results show, in terms of greenhouse gas emissions savings per ton of material recovered, that durable goods have a lot more beneficial impacts than all the other materials. That doesn't mean we should stop recycling. That doesn't mean that, even because the mass of recyclables is much, much bigger than the mass of durable goods. But maybe we should be focusing on durable goods instead of food waste, let's say. And so considering viewing from a point of greenhouse gas emission savings per dollar invested, durable goods is also the best option. So if our hypothesis is right, maybe we should be starting focusing on the recovery of durable goods in terms of greenhouse gas emissions. I'm not considering any water or nutrients or anything like that, but for in terms of greenhouse gas emissions, durable goods is the best option. And I think that's it.
That's our transition.
Okay. Yes.
So first of all, what I'd like to do is let's thank Malik and Carson and Beatrice for what you're doing. I just am fascinated by that one slide about, because I mean, human nature here is that I'll go to Goodwill. I think a lot of us go to Goodwill. But I also know that when I'm in a pinch to get rid of stuff and you're on that weekend cleanup, there are times when you end up throwing away things that you're just like, wow, if I'd have planned better, I'd have gotten rid of this or given away. And then the second thing is that we hold on to stuff so long. And one reason is, well, I'll take that and donate it, but I'll stick it in my closet for now until I get to that. And before you know it, several years have passed. And it's not worth as much anymore. The idea that someone will want to use it goes down. Its value is not as great. And so even though it sounds kind of crazy, I mean, based on Beatrice's results right now, I'm not talking about pure cost, I'm talking about if your goal was to find the most cost-effective way to reduce greenhouse gas emissions, for example, it would not be to do food waste collection.
I'm not saying anything wrong with food waste collection. It would be to literally send a truck around on a route through the neighborhood picking up materials so that they could be refurbished. And she's still got to kind of refine all the numbers and everything, but I think it's part of this whole kind of evolution of the way we're thinking about our materials and how things put together. So with that, we've got maybe 4 minutes. If you in here wanted to ask questions. Now, actually, I'll say it like this. For those of you in the room, I'll stay as long as you want. The students will stay, I hope, as long as you want. We can talk about it. But if you had anything that you wanted to bring up, or I'll check the chat screen real quick. Maybe if we, I see David's question that we answered earlier, but if anybody online, if you're still there, want to ask anything, we can go ahead and address that now. And we'll plan on probably stopping recording, though, in about 3 minutes or so. So anyone online? Or you can go ahead and just ask the question. We can hear it on the speaker pretty well.
Dr. Townsend, this is Richard. Hey, you guys are going to be sending some kind of a, didn't you say you had, I think Malak had talked about having some kind of presentation to send out, and also there was a couple of papers mentioned. I think, are you going to be circulating those, or what was the plan on that?
Yeah, Richard, absolutely. So what we'll do is we'll send or make available a copy of all the slides so you can have them. And there were several handouts. They related to some papers that we've published recently on this subject, based on the Hinkley Center funding. And then there was a handout which was from the WARM model, which we can send you, but I think you might also have it from another meeting that we've handed out too. But absolutely, we'll send those to you. I appreciate you asking.
Yeah, and one other quick comment is I kind of have a feeling that Bill Hinkley is somewhere smiling.
Yeah,
So,
I think so too.
Yeah, I know he's enjoying this.
Yeah. I appreciate it, Richard. Thank you.
Yeah.
Okay, so I'm going to go ahead and right now stop the recording, and thanks to all of you who listened in. I've got to figure out how to stop the recording though.